Hello, everyone. I'm very honored to give the presentation. The topic of my presentation is research on small signal modem of VSC-HVDC system based on modular multilevel converter. This presentation includes 5 parts. The first one is background. As more and more MMC HVDC projects put into operation, the associated resonance problem become common, such as the Lucy projects. The current resonance mainly appear under balanced grid conditions. In some special case, the resonance problem under unbalanced grid conditions emerge, such as in Zhangbei, and should also be paid attention. HVDC grid should be able to operate under unbalanced AC faults for the following reason. The first one is MMC is very possible to connect the island or weak grid in the case of such as sending the wind energy out. MMC may operate under unbalanced grid conditions for a long time because of the weak grid conditions. The next one is the inertia of MMC is very small for the typical cascaded control structure with inner loops. The time constant of the inner current loop of MMC is usually 2 to 5 milliseconds. However, it usually takes about 80 to 200 milliseconds to clear the AC fault clearance. HVDC must be stable before the AC fault is cleared. That means the MMC must operate even after fault occurs, which will cause the unbalanced grid conditions. The next one is the requirement of the fault read-through ability. In real project, MMC is indeed implemented with negative sequence controller to satisfy the fault read-through requirement. Usually, the current reference of negative sequences is set as 0. The purpose of the research is to ensure the stable and safe operation of HVDC grid under AC fault to avoid the resonance and violation of other constraints. The AC fault of one MMC cannot disturb the operation of other MMC station or the even entire grid. The research content, the first one is the small signal model to accurately reflect the stability of the real system. This part includes 3 parts corresponding to the component of MMC grid. The small signal modem of MMC, DC cables, and the entire HVDC grid. The second one is a reduced order model to improve the simulation and analyze efficiency. The third one is the post-fault control to online autonomous limited the operating point and to guarantee the safe operation of MMC. It includes the steady operation region, the modular structure to apply the post-fault control. MMC is divided into the part, the electric part and the control part. For the electric part, the well-known average value model is the basis to analyze the MMC. As shown in this slide, each arm is equivalent to a controllable voltage source. Each voltage source is coupled with a controlled current source. The following two equations refer to this average value circuit. Since there is multiplication of different components of variable frequencies, there will be harmonic coupling effect. The common express is like the formulas and the table. X and Y are the variables containing various frequencies. X times Y can contain the constant value plus A, B, C, D, and E. For MMC, the harmonics and the state variables are listed in the table, including the harmonics up to the third. Because of harmonic coupling, component A also includes positive, negative, and zero sequence components. According to the relationships of the harmonic order of X and Y, the sequences of components of X times Y can be classified as in the table. After clarifying the sequences of various components, the X times Y can be transformed into DQ frame by universal Park transformation. For different frequency and sequences, the Park transformation is different. The typical control part of MMC include the PLL, the positive sequences, the negative sequences in the current loop, the negative sequences and the zero sequences circulating current suppression controller, outer control loop and measurement. Compared with the electrical circuit, the small signal module of the control part of MMC is easy and straight. Combining the electrical and the controller, the small signal module can be expressed in the form of this slide. The DC network is composed of DC bus and DC cables. For the DC cable, especially when the DC cable is long, the cable parameter per unit is dependent on frequency. It changes with frequency. To reflect the frequency-dependent characteristic, the frequency-dependent line model is used for small signal modeling. The frequency-dependent characteristic is simulated by classic pi section, and each pi section is composed of several parallel branches. The parameter of resistor and the inductance of parallel branches is obtained by curve fitting from the raw data of simulation model. The more branches, the more accurate the frequency-dependent characteristic. As we can see, the impedance of model with 1 pi, 5 pi, and 50 pi sections are compared with the simulation model. It can be seen that the model with 5 pi is consistent with the simulation model up to 2000 Hertz. And the model with 50 pi is almost consistent with simulation model up to 10,000. And the model with just 1 pi section is not acceptable because the consistent range is just up to 200 Hertz. Because there is double line frequency DC current and voltage at DC side when the AC fault occurs. The small signal module of DC network sending the double line frequency component. In order to get a uniform expression, the DC component and the double line component is considered separately for DC line and DC bus. For DC line, these are inputs, which represent the DC and the double line frequency components of bus voltage. For DC buses, these are inputs, which represent the DC component and the double line frequency component of DC current inject from MMC station to HVDC grid. Combining the DC line and the DC bus, the DC network small signal model can be expressed in a unified form. The inputs are also the DC current inject from MMC section to DC grid. When connecting station model and the DC network model together, the variables of different stations must be synchronized. As we can see, there are 4 MMC stations and they are connecting through DC grid. For example, the variables of station 1 is located in DQ frame with rotating angle omega t plus theta 1. Where variables of station 2 is located in the DQ frame of omega t plus theta 2. So when establishing the small signal model of station 1 and station 2 in one common frame, the variables of 2 stations must be synchronized. For the case of MMC HVDC grid, omega t is chosen as the common DQ frame. All variables are transformed to the common DQ frame of omega t. For DC components of DC current and DC voltage, it has nothing to do with the transformation. They can just connecting each other directly. The transformation just refers to the double line frequency components of DC voltage and DC currents. For example, the DQ frame 1 is leading DQ frame 0 by theta. Then the relationship between two frames can be expressed, and the small signal variable can also be derived. After the synchronization of last slide, the complete small signal model of HVDC grid is constructed in a modular way. For a test system with 3 terminals, we can see the thematics of established small signal model. The proposed model is compared with the simulation model in PSCAD. The red curve is the proposed model. The blue curve is the simulation result. We can see that the circulating currents of two models are constant. The proposed model can accurately reflect the dynamics of the HVDC grid on the unbalanced fault. The lower diagram shows the eigenvalues calculated from the proposed model. We change the proportional index of the PI controller from 5 to 100. We can see that as the dominant eigenvalue will move from the left plane to the right plane, the critical value is about 14. When k equals to 14, the real part of dominant eigenvalues is around 0. The blue curve is PSCAD simulation curve. For the first one, k changes from 5 to 40. The DC current is still stable. For the second one, k changes from 5 to 45. The DC current will gradually become unstable. So the proposed small signal model of HVDC grid can accurately predict the stability of HVDC grid. For one MMC station, each small signal model has around 40 state variables. So when integrating one entire grid, the order of the entire HVDC grid will be very large. To improve the simulation and analyze efficiency, the order of HVDC grid should be appropriately reduced while maintaining the efficient accuracy. The universal order reduction method is shown in the flowchart. First, we establish the 4-order model of MMC, then calculated the eigenvalues, judged the system is stable or not. For stable and unstable system, calculate the matrix, Green matrix, and then determine the non-singular transformation matrix T from of the system, distinguish state variables according to Hankel singular value, and finishing the reduced order small signal model. The first diagram shows the frequency response of a singular value of a reduced order model with order of 4, 6, and 8 for 1 MMC. We can see that the reduced order of 4 cannot reflect the characteristic above 1000 Hz. The second and the third diagram shows the DC current for a small power and DC voltage disturbance. The gray one is the simulation result from PSCAD. As we can see, the blue curve is from order of 4. The deviation is obviously different from the others. The order of 6 and 8 are both consistent with the simulation. There are 2 kinds of reduced order models for the entire HVDC grid. The first one is the distribute one. In the distribute model, the concerned MMC used the full model. The DC network and unimportant MMC use their own reduced order model. For the integral model, the DC network and the unimportant MMC use one reduced order model. For a 3-terminal HVDC grid, the full model has 2008 state variables. The model can be reduced to 19 and 16 order as we can see, all reduced order models are consistent with the simulation. For instability protection, the proportional index of PI controller is changed from 3 to 5. We can see that the critical value is 3.8. When k equals to 8, the real part of eigenvalue is 0. The dark point is the eigenvalue of 4 model, and the red one is the result from the reduced order model. We can see as the eigenvalue move to the right plane, the reduced order model is more accurate. The dominant eigenvalue of reduced order model is almost the same with the result from the 4 model. The lower diagram is the power when k changed from 3 to 3.8. We can see that the power gradually diverges. So the reduced order model can precisely predict the instability of the system. This part is about how to control MMC after fault. First, the fault condition is studied. We assume C phase is grounded. Then the C phase AC bus voltage will be unbalanced. The magnitude will be smaller, and there will be a phase deviation. The known information is the active power, reactive power, because it is determined by MMC controller. The source voltage amplitude and the system impedance, the fault information, the location of fault, and the ground impedance is also known. The unknown information include A phase and the B phase AC voltage amplitude, and the C phase AC bus voltage amplitude, and the C phase voltage phase deviation. We have 3 unknown variables, and to solve the 3 unknown variables, we need 3 conditions. KVL for A phase and C phase, and the third one is balanced because of the MMC control. For determine the AC fault, we can calculate the bus voltage information with the bus voltage as input. We can determine the operating state of MMC. To determine the operating region, we have to identify the constraints we have. For example, we have the regular constraints for conventional VSCs, including the converter rating, modulating index, transformer rating, and AC current, and so on. However, for MMC, we should pay attention to the inner variables of arm currents and submodule capacitor voltage. Because of arm current and capacitor voltage contains the harmonics of various sequences. They have very complex waveforms, and it is difficult to get the peak value. So we can use the scanning method to seek the peak value. For example, when we know the formula of arm currents and capacitor voltage, we can scan the non-sine waveform from 0 to 2 pi with a small step because they are periodic, and keep the maximum value and repeat again. Finally, we can get the peak value of non-sine waveform. After we get all constraints, we have to draw the operating region because it is very difficult to drive the mathematical expression of arm current and the capacitor voltage. We can use the point scanning method. We just check each point in the possible region and keep the right point. The right diagram is a typical operating of MMC, considering arm current and capacitor voltage. The right one region is confined by arm current and capacitor voltage. The region confined by red curve and black curve are the operating region determined by the regular constraint. So the actual operating region is smaller than regular constraint. In the left diagram, the red region is operating. The operating region, the red region is the operating region of MMC after fault. The black curve region is the operating region before fault. The operating point before fault may be outside of the allowable operating region after fault. We must make sure that even after fault, MMC can satisfy each constraint. For example, in the normal state, MMC at 0.1, it is okay because it is inside of the operating region. However, after the fault, 0.1 is outside of red region. It is not okay because it is outside of the operating region after fault. To control the MMC automatically, we can use a post-fault control to limit the MMC automatically. The normal state is P1 and Q1. When fault occurs, assumes that the capacitor voltage constraint cannot be satisfied. Then the PI controller will output a value, which means the distance and the 0.1 should move towards the red region. Then the new point will be calculated based on 0.1 because we have known how far the 0.1 should move. This controller is modular because we use the max function here. We can guarantee only one constraint is activated. The right diagram shows one example of the post-fault control. The limit of capacitor voltage is set to be 530 kilowatt. Before fault, the capacitor voltage is close to it. The power is equal to its reference. After the fault, if the power keeps the same, the submodule capacitor voltage will increase to 543 kilowatt, which is obviously bigger than its limit. After the post-fault control is activated, the power changed to a small one. And in the meantime, the capacitor voltage decreased to its limit, equal to its limit. In this way, we can make sure each constraint of MMC can be satisfied automatically, even after fault. The next part is hardware experiment platform. We are building an experimental platform of hybrid MMC. An MMC controller based on FPGA is designed and manufactured, which contains two levels of controller. The inner and the outer double loop controller, voltage sequencing, carrier phase shift modulation, and the NLM modulation algorithm are programmed use Verilog on FPGA of Altala. It has short control delay and strong expansion ability. The integrated 4-bridge submodule power board is designed and made, and the IGBT driver measurement, protection, IGBT and energy storage capacitor are integrated into one PCB. It has 3 kinds of voltage output to form a hybrid MMC. That's my presentation. Thanks for your attention.
Okay, thank you very much for your amazing presentation. So now if you have got any questions to Mr. Dong Li's presentation, please feel free to unmute your microphone or raise your hand.
I have a question.
Yes, please. Please introduce yourself and then ask the question. Thank you.
Hello, my name is Gumeng. I have a question. What do you mean by coordinating synchronization when you establish a small signal model?
Thank you. The synchronize of the different coordinates First, the coordinates of each converter station are different. They are adjusted based on the DC lines. In addition, the DC lines, the DC voltage and the DC current contain not only the DC component, but also double line frequency component. These components need to be transformed. Each converter station is the difference of the Park transformation. The angle of the transformation is different because of the frequency is only the phase is different. If we take the DC line as the benchmark, we can determine the phase angle difference between each converter. By rotated matrix, we can synchronize the different DQ coordinates. That has an advantage that we can easily add more converters. If each part of DC network is modeled separately, the small signal model of DC network can be established modular. If I made it clear.
Yes, thank you.
Okay, thank you very much for your question. Is anybody else have further questions?
Hello, I'm Li Bowen. I want to know how is the post-fault control implemented and how to adjust the operating point of the MMC.
Post-fault control.
Yes.
The post-fault control, first we measure the variables that we care about, which are likely to exceed the limited, and compare them to their limited. When they are found to exceed the limited, the PI controller is used to control the operation point move into the right region. When the controller is activated, the active and inactive power values varies in proportion. In general, it is moving from null to the origin. How far it moves is determined by the PI controller. The PI controller outputs the move distance, so we can make sure that the operating point is in the right region. This approach is maybe not the best because we are not considering active and reactive power separately. For example, if we want to keep the active power constant, we can just move down the operating point and only reduce the reactive power. And the same, if we want to keep the reactive power constant, we can just move right the operating point. How to achieve the optimal control, how to combine the external requirements. That's one of the things we want to look at later. Thanks.
Okay, thank you.
Okay.
Professor.
Questions?
Yes.
Yes.
Sorry, because I will catch up with another very urgent thing after a while. So may I firstly ask a question and then I will have to quit the meeting.
Definitely, please do so. Thank you.
Yes, because we can see that Mr. Li Dong has done very comprehensive work on the modeling of MMC-based HVDC and proposed some control schemes of that. But because the name of our group is low inertia system control, so I would like to ask a question about on the system level. So I would like to know whether MMC-based HVDC can be can help improve the frequency and voltage stability of the future low inertia power system, because the inertia of the power system is becoming lower and brings challenges to frequency and voltage stability. So can you maybe say a few words about that? Thank you.
Thank you. About the frequency support and such thing, I think a lot of power electronics will make the system become more weak, not only because they are easily to break down, but there are inertial problems involved. Without special control strategies, power electronics system cannot provide the inertia to the system as synchronous generators do. Because they don't have the they don't have the mathematical inertia and the energy of the rotor and such things. And the switching devices are open and close very quickly and only accept the order of the controller. But I think the converter has one advantage, that is it has more stronger control ability. We want to look at how we can use the better control ability to make the grid stronger. For example, we can use the energy storage in the capacitor in MMC to provide inertia support to the grid. If the energy required is more large, such as frequency support, capacitor energy is not enough clearly. So we need to coordinate the control of wind, such as wind farm, just the other side of the HVDC, such as wind power and the converter stations, or even the multi-terminal VSC-HVDC system to find the energy that we need to provide support for the system. That's my opinion.
Okay, thank you very much. Now I have to quit the meeting, and I would like to thank you all for participating in this event. Thank you very much. Thank you, Professor.
Before you move, I would like to point out that without Bao Weiyu, who will now move to another meeting, but also without Shi Jianhong, the entire organization wouldn't be so smooth. So let me express my thanks to both of them, to Shi Jianhong and Bao Weiyu, for their help and support in organizing this meeting. So Weiyu, goodbye, and bye-bye. Have a good next meeting. And let's move forward. Further questions. I have some questions, but just asking the audience. Couple of things. Yes, Piotr, just as, okay. Let's now ask.
You go first.
Yeah, please.
I have some technical. No. I have some technical questions. So you go first.
Oh, thank you very much. Well, actually, it was indeed a technical question from my side. Dong, you worked on short circuit studies. Can I ask you, how would you describe a short circuit current on a voltage source converter HVDC transmission line? What are limitations from the perspective of magnitude and its waveform? And we are aware that these short circuit currents have a different quality, quantity compared to classical short circuit currents on high voltage AC transmission lines.
You mean the fault situation difference between the MMC HVDC and the
in time domain, how this short circuit current looks like?
I think when the fault occurs, the HVDC grid is more badly. We know the power electronics devices is easy to break down, and the fault is very fast. So additional equipment is needed to clear the fault, such as AC breakers and DC breakers or converter stations with fault clearance ability. The AC breakers is slower, but the technology is mature and cheap. The DC breakers have good performance, but it is costs too much and not being widely used. Some converter stations, such as 4-bridge submodule MMC or hybrid MMC, have fault clearance ability, and I think they are better choice to deal with the fault in the HVDC grid.
Good, thank you very much. Professor Vorobiev from Skoltech University, please, if you'd like to ask a question.
Yeah, so I have, well, first of all, let me say that it's very technical study. Yeah, I have some number of questions. I'll just try to be brief. So if you could go to the slide where you show the network, like you model some number of HVDC terminals, as far as I understand. Yeah.
This
yeah,
one?
this one. Yeah. So there are 3 terminals that are connected through the DC cables, and each of these terminals is connected to the AC grid. Is it correct, or I'm missing something?
Yes.
So, but do you really consider this connection to the grid? Like there is a current controller, but there is also a PLL. Do you consider that in your model as well?
No, it's a simplified model, just for a small signal module of HVDC grid. We just consider ideal ideal condition.
So you're considering that like the DC part, yeah? So this
yes.
The instability. Okay. Then I had another. No. I mean, it's clear to me. So the instabilities that happen, they happen inside of these DC cables. Is it correct?
The instability of the system is not being studied. We just try some values to reflect the stability of the system, to make sure that the small signal module we established is constant with the simulation model in PSCAT.
Okay. But then returning back to the DC cable model, because you had a slide on this, something that is called a long line model. So you say that you can represent your line as a series of pi sections, but there is a continuous limit to that. Why don't you use it? Because whenever you use this model that contains a finite number of pi circuits, you will always have problems at the higher frequencies, as you indicate. So you see, when you increase the number of pi sections, what you have is you move these inaccuracies further in the frequency. But you can just take the continuous limit. Did you try that?
First, we used a very simple model of the DC network, and then we found that the model is not correctly. So then we find a way of establishing the DC current model by the pi section, and we just find the more pi section we used, the more accurately the small signal model of HVDC is the accuracy of the DC grid is more. But
what one can do is one can go to the continuous limit, and then you will get something like a telegraph equation, and from that you can get the response of the DC cable, which will be correct at all the frequencies.
Yes.
So
yes.
it contains like some hyperbolic functions, but it's like a more or less known approach. You might want to try that because it will not limit you in frequencies at all. Yeah, and then I had another. The last question is about this simplified model. It's slide 11, if you can go there.
11.
Yeah.
Oh.
This one. Yeah. So what is a gram matrix? I'm not sure.
This part job is not what I done. I just can generally say that the reduced order model is to reduce the reduced order model is just reduce the order of the original system and return the leading eigenvalues and some important state variables for the original system.
So you're using some kind of Hankel truncation for that, as far as I understand, yeah?
Yes, just by calculating the important eigenvalues and
how do you choose them? Like, because you've got a lot of eigenvalues. How do you choose which ones to cut and which ones to leave?
The single value is arranged in order of importance, and the judgment of importance and unimportant, I cannot answer you because this part job is not mine.
So the only thing about this this type of model reduction, which is important, is that it's very sensitive to the system parameters. So what I mean is that, for instance, when you do that, you get the model, and this reduced order model is fine, but it's fine as long as you keep all the system parameters fixed. Once you start changing them, well, basically what happens is that once you start changing the parameters, then the order of those eigenvalues start to mix, and then you might get in a situation when you get a reduced model and then you use it with slightly different parameters and it doesn't work. Or another thing which is sometimes tempting is to use the matrix in order to find the stability boundaries, and that can lead you to troubles because when you try to find the stability boundaries, you kind of assume that your reduced model is correct over this whole region of the parameters, but it's not always the case. Did you see any kind of things like that? So when your reduced order model starts to give you bad results compared to the full model?
Yes, I think if we change the parameters, it will inflect the reduced order model and makes the result different, or the result is not correct. We are trying to fix this.
Okay, and then just the very last question. Do you have like this reduced order model which we can just see? Is it like compact enough to see it, or it's still like a big matrix type of model?
It's very complex matrix.
So it's still complex.
Yes. About half reduced, 200 to 100.
And what about the time scales? Like, what is the fastest time scale in the original model, and then the fastest time scale in the reduced one? Because this is also important.
The time we used is smaller. The time we take is smaller, and the reduced order module of the HVDC grid can apparently shorten the time we use.
No, I mean the time scale, like the degrees of freedom. Because when you reduce, you typically get rid of the fastest time scales.
The time scale.
Yeah.
We didn't notice that situation.
Like a bit about half of the original time spent, or like 1/10.
So in other words, you cut all the fast time scales and you get to the time scale which is 10 times slower than the fastest one. Is it correct? The understanding?
It's a kind of correct. I don't sure that if we are talking.
I mean the reason I'm asking is very practical. because the fastest time scale in the problem determines the speed of numerical integration. So when you feed your model into a numerical engine, like in MATLAB, for example, or anything in PSCAD works the same way. It starts to integrate, and if you have some fast time scale in your model, even if you are not interested in this particular variable, it still slows you down. You know, that's why I'm asking. So what is important is that how good you were able to eliminate all the fast time scales. That also it is important for this reduced order model. Okay. Yeah.
Okay, we will working on that later.
Thank you, Piotr, for these questions. Professor Vorobiev is specialized. I don't know for what Professor Vorobiev is not specialized, considering his background in chemistry, physics, electrical power systems, power electronics, control, monitoring, and he's also a passionate singer, by the way, covering also quite a broad range of topics. Well, we have some further questions. It is Mile Mitrovic Skolpek, currently in Germany. Mile, welcome. We can hear you. Please act. Somehow your microphone is not.
Do you hear me now?
We hear you now. What means that you should select what will be the target. It's now good. Yes, please.
Okay. Thank you for presentation. I would just to continue question of the Piotr. He asked about Gram matrix, and I can briefly explain what is Gram matrix, what is exactly the difference between Gram matrix and covariance matrix. Briefly, covariance matrix, it is like distance between features or different variables, and Gram matrix, it is distance between samples, and it is just a difference. Of course, we use both matrix for calculating eigenvalues of eigenvectors, but it is just a difference, and it's all what I want to add.
I'm sorry for this part. I cannot discuss with you because this part is our library's work, and I didn't participate it a lot. My research is more likely at the control and active control of transient and steady state of the HVDC system based on MMC, just like the third part and the first part. The second part is not my, I cannot discuss with you.
Okay.
Sorry.
Okay, just was comment to Piotr question. Thank you.
Yeah, thanks a lot.
It's very good.
Yeah, thank you very much
Let
for your
me check
explanation.
if these are some further comments. Also some nice
If not, let
greetings.
me ask a question.
Yes, Joe Young,
I
Professor Joe Young asked question. After that, Jiping Kong. Joe Young, please go on.
Yeah, because I'm doing presentation and now I'm also
A little bit louder,
It's not to estimate the transient behavior. Okay, can you hear me now? Hello.
It is now
Yes,
much more better. Thank you.
Okay. So I'm doing research on dynamic state estimation, which is to estimate the transient behavior of the states. I can see a lot of transient behaviors, lots of different signals. So I'm curious if maybe in the future I will do some dynamic state estimation of the system with HVDC. So which kind of transient behavior do you think is
We have a problem. At least I cannot hear you. I can hear you now. Okay. Can you repeat the question again, Joe Young?
Okay. My question is, which kind of transient behavior do you think is the most important one that was to give special focus to monitor it.
Yes. The transient dramatics. It is a fault condition. When the
Fault
fault
condition.
Yes. When the fault occurs, how to make sure the MMC is safe and the devices in the grid is safe. One point here is that after a fault occurs, although we can control the active and the reactive power of MMC, and we can make the MMC operate at the safe operation domain. The power delivered from the HVDC, as I said, we cannot control. For example, the wind power is sent through MMC. The output power of the wind farm may not be controlled in time. So we need to look at the coordinate control, how to deal with the extra energy, make it more safety. That's one of the research we are interested.
So can you show me the transient behavior of the fault condition as you have mentioned? So how does it look like? Yeah, the response of the fault condition.
The sense, I think, is the wind energy sent out through MMC. So the fault condition, maybe the DC fault, the wind farm fault, the grid fault, and such as this thing. The grid fault.
So for the fault, maybe we should need to monitor the currents, right? The currents in the maybe HVDC side, right?
Yes, the AC fault occurs, the voltage down, the current is increased very quickly, and the power cannot be sent out smoothly, and it all maybe occurs very bad situation.
Okay, thank you very much. Is there any more questions? Now it's 6. We still got maybe
I thought that there was one more question. I thought I saw.
Yes. By Gong Yiping. So please unmute your microphone.
Okay, let's consider this question as the very last question. After that, we'll make a joint photograph. Thank you, please.
Hello, Lido. I'm enjoying your presentation very much, but I have a question. I want to know what difference does it make if you consider MFCs the operating regime, about the operating regime of MMC.
The operating region. The operating region, consider the operating region of MMC will make more accuracy of the operation region. In the field, we must to make sure the inside MMC variables cannot exceed the limit. The conventional region, operating region, just consider the outside conditions, and now we make the MMC inside conditions take into consideration, and such as arm current and capacitor voltage, and we will find that the operating region is become smaller, and that means the operating region concerning about the MMC is more accurate.
Okay. Oh, thank you, Ms. Lido.
Thank you.
Thank you very much. It looks that we can slowly finalize our Friday seminar series. This is the very last seminar, and let's express our congratulations and thanks to Dong for brilliantly expressing and delivering his presentation. Thank you very much for this. Well done.
Thank you, Professor.
Furthermore, also warm welcome to participants from Finland. What's also very nice. Now, would you be, Mazaher? Nice to see you.
Oh,
Great.
Mazaher.
Yes.
Long time no see. Nice to see you.
Very nice.
How are you?
Hello, everyone.
Yes. Nice to see
Where are
you.
you now, Mazaher?
Yeah, Finland, Joyan. Sorry,
Finland.
yeah.
Wow. Nice place. Yeah.
Do you also have some snow in Finland, like we here in Moscow?
Exactly today we got the snow.
Very nice. It's so nice.
Yeah.
Very nice. Thanks. Brilliant. Well, those who have camera, I'd appreciate very much if you start your camera so that we can make a joint photograph. But let me double check who will do that. Zhou Yang, will you do that, or it will be done by Wei Yu, who is not with us, but he cannot.
大家把那个摄像头打开一下啊。
Mustafa, nice to see you.
Thank you very much. Nice to see everyone.
Okay, it's also nice to see.
And hi, Mazaher.
这个是最后一次了，大家把摄像头都打开啊。
Hi everyone.
Stepan, Mile, Piotr, very nice. I'm really very happy that we had this seminar series, and I'd like to point out that resulting from this seminar series, we will publish a monograph in which all presentations will be assembled into a single document. Each presentation will be followed by a 2-3 page summary of the presentation, so that we'll have a trace of our work in year 2022, which is a year which we will definitely never forget from a number of reasons, but also from our monography. So, Zhou Yang, please organize now the formal creating photograph. Thank you. Smile. If Zhou Yang is doing that, it might last a couple of seconds. And it must need extra couple of seconds as well.
Yes.
I made also a couple of snapshots and videos just in case.
Joyan, is everything all right?
You are muted, Zhou Yang, so if necessary to legend.
Okay.
Vladimir,
so now
I like your comments as well.
Sorry, I muted my microphone. So now I have got two very good photos, and I have sent one of them to you.
I see unable to download the image. I don't know. Maybe it's
maybe it is too large.
Oh yes, there must be challenges. I know, but we'll resolve them anyway. Thank you so much. I'm very happy to see all of you from China, India, Russia, from Europe, and I wish you all the best. And this is not, as I said, the end of the work. Our next step is to prepare this monography, and this will be also nicely organized, also supported by Wei Yu and organizers. Thanks in advance for your help and support. Thanks for your contributions. Next year, we move forward. And Mustafa, please add something what you'd like to say. And everybody is now can give any comments.
Yeah, first of all, thank you very much for organizing this activity. It was very informative during these last couple of months. I really enjoyed it. And second, I'd like to inform that our research group at the University of Warwick is recruiting a postdoctoral research fellow. and we have advertised it online. So you are most welcome to check it, and if it fits your research area, apply for this position at University of Warwick. And we will be happy to receive your applications as well. And the third, I personally look forward to another seminar, probably maybe next year or anytime later on. So please do inform me as well. So I'd be happy to listen to excellent presentations. Thanks again for all your hard works present.
Thank you, Mustafa.
Thank you.
Is there any further comment? I can say that this entire work has really impressed me, particularly from the perspective of your knowledge, from the perspective of your enthusiasm. And I was very happy to see all of you from Skoltech, from Russia, from Moscow, all of you from Shandong University, from Jinan, our guest speakers and attendees from New Delhi, from Kanpur, then from Finland, from Delft, Holland, from Belgrade, Serbia, and from Singapore as well. So this is really something what all of us can be proud about. And I'd like also to express my thanks to Zhou Yang Jin, my former PhD degree student, now a professor, and also Professor Ding Lei, who was one of those who has strongly supported. He's the dean at Shandong University, and also my former postdoc, and one of excellent professors working on different research areas and research topics. Naturally, I would like to express my thanks to members from Skoltech, Professor Vorobiev, Professor Elena Grazina, Professor Federico, has a long name and surname, I must learn it, Martinez Sanchez, and also to all of you. Without all of you, it wouldn't be that successful seminar.
Yeah,
thank you very much. Yes.
Thank you very much, everyone.
Yes, Zhou Yang, please formally close the session because you are the host. Thank you very much.
Okay, so this session will be the final session of the distinguished series this year, and I would like to express my sincere gratitude to Professor Vladimir Terzia for organizing this fantastic series. I really got lots of useful information from this series, and also we had lots of interesting conversations between the speaker and the guest. So now I am honored to announce this year's distinguished speaker series is concluded. Thank you, everybody. Attend this series. Without you, it would not be successful. Thank you.
Thank you.
And,
goodbye.
Thank you, everyone. Bye-bye.
I would like to wish everybody a very nice weekend, and see you probably next year. I am looking forward to more exciting, amazing lectures next year.
Bye-bye.
Bye-bye.
Okay, bye-bye.
Bye-bye, everyone. Bye-bye.
Bye.